tell you, I'm usually quite risk averse, but from time to time I have been known to do something stupid. And one of those times was about 10 years ago when I volunteered to be hit by a taser gun. And this was before the London's Metropolitan Police had taser guns. It was before the UK had done any safety testing on these things. But I got the opportunity when I was writing a story to try one out for myself, or to have one tried out on me, in fact. And I became the first person in the UK to be hit by a taser gun. That was very painful, as you might imagine. And it was slightly disturbing, but it was nowhere near as disturbing as the thing I kind of want to introduce to you today. And that is this. It doesn't look like much. It looks like a kind of cartoon key. But this is called transcranial magnetic stimulation. And just a couple of years ago, I tried this out as well. And for my money, it's much worse than a taser hit. This is effectively a very crude remote control for a person. You can use transcranial magnetic stimulation, which basically applies a magnetic pulse to your brain to make people move their limbs, and to make people move their fingers, and to make people lift themselves out of depression, in fact. There are trials going on at the moment. You can make people feel more empathy. So it doesn't just control you physically, it actually controls you mentally and emotionally as well. And if you get some fine control over this rather crude device, then you could actually use it as a kind of way of making a person your puppet. So I submitted myself to this because I was trying to find out what was going on with a very strange scientific result. Now, this result was found in 1997 by a man called Benjamin Libet. And what he discovered was that if he wired up somebody so that he could read their brainwaves, he could actually see their intentions before they even knew what their intentions were. This is Benjamin Libet. He died in 2007, unable to deal with the consequences, actually, of his discovery. And he hated this discovery. But what he found during his experiments was that he could watch somebody decide to do something, and he knew before they had actually decided, or before they became aware that they had decided, what their brain was about to do. So he could read their brain, he could read their mind, and he could tell what was going to happen. And this was just a few fractions of a second before actually they became aware of what they were about to do. But what Libet's experiment showed is that actually we don't have the free will that we thought we had. And Libet hated this, and perhaps for very good reason. He was horrified by it, and it's now being used in courts sometimes as a defense. People are arguing, my brain made me do it, on the basis of this kind of neuroscience. The thing about this is, it's a very strange result, and you could call it horrifying. But actually, you can also see it as the key to understanding what is human consciousness. And we're trying to find this out. And this is a kind of a huge step forward. Discovering this kind of intention to move is visible before people are even aware of it. It kind of gives us a clue to consciousness. And this kind of strange scientific result actually happens across science and is absolutely vital to the process of science. It's in every area of science. If you haven't found something strange, then you haven't really got much to work with. And that's why Isaac Asimov came up with this great quote. He said, the most exciting phrase to hear in science, the one that heralds the most discoveries, is not Eureka, but that's funny. And this is how science works. And so I was in this basement laboratory having my brain manipulated because I was wanting to find out what anomalies, what strange things are happening in science today. What is making scientists say, that's funny? And this question of free will was one of them. But these things are incredibly important. If you look at the history of science, what you find is that these things matter time and time again. So a strange observation in the way the electron radiates energy actually led us to special relativity. So if you look at a still electron, it radiates a particular characteristic of electricity. If it's moving, it's slightly different. And at the time when this was discovered, there was no theoretical basis for it at all. Nobody could understand why this could be, until Albert Einstein came along and decided that actually this would make sense if you could just show that space and time are completely different to how we think, and that there is a maximum speed at which anything can move in the universe. And this is special relativity. And it came as a result of seeing an anomaly. There was another anomaly at the turn of the 20th century. Seemingly very humdrum observation was that if you have something that's at a particular temperature, it will radiate a particular spectrum of energy. And it doesn't matter what that thing is. So if you're baking a cake in the oven, that cake, you take it out at 200 Celsius, that kind of agglomeration of proteins and carbohydrates will radiate exactly the same spectrum of energy as the inside of your metal oven. Now, this made no sense to anybody at the time, but it was actually solved by a man called Max Planck, who showed that you could solve this by saying that energy is actually not infinitely divisible, but divisible only into something he called quanta. And you can have a quantum of energy, and you can't go any lower. And from this, we got the whole of quantum theory. And quantum theory, of course, has brought us everything in the modern world. So electronics, iPods, the internet, your mobile phone, everything comes from this seemingly humdrum but strange observation about the radiation of heat. And I could go on. There are more examples. Continental drift, for example. Plate tectonics came from strange observations. Somebody said, "That's funny." And this is so important in science today, and sometimes gets forgotten, that actually what we need to do is look for the things that make us say, "That's funny." The trouble is with the things that make you say that's funny, is that they actually are quite horrifying at various times. So let me show you this man. This is a man called Brian Schmidt, and he is actually, I think, this week collecting a Nobel Prize for physics. He's collecting it because he helped discover dark energy, which is actually a euphemism for stuff we know nothing about, but seems to have some effect on space and time. It makes the universe accelerate ever faster, expand ever faster. So we have a universe that's growing, and that rate of growth is accelerating. And Brian Schmidt was one of the men who helped to make that discovery. Now, what he said to Science magazine about that discovery, his reaction to it, he said, was somewhere between amazement and horror. And if you're going to face the things that don't make sense in science, I'm afraid that like Benjamin Libet and like Brian Schmidt, you may well find yourself to be rather horrified. Now, we have plenty of other examples of stuff that doesn't make sense in science today. So as well as this dark energy, which actually makes up 72% of the universe, that's stuff we know nothing about, there's also another 24% that we know nothing about called dark matter. And that was actually discovered in 1933, or rather, the need for it was discovered in 1933. And that seems to be some kind of particle that interacts through gravity and nothing else. And we've been searching for it ever since. And people are quite horrified that we haven't found it yet. And especially when you consider now that that means 96% of the universe is actually missing. So it's not just physics, of course. In biology, let me tell you, there are various problems. One of the anomalies of biology is biology itself. So life doesn't really make sense. Life is an anomaly in that we don't know what it is that makes chemicals come together and become alive. We don't know what life is. We don't know how to create life. And we've tried on many, many different occasions to put chemicals together and create this thing that we all know is life, but we don't know how it arises. And we don't know of any other examples in the universe where it arises either, which makes life slightly difficult. The story of biology, the story of life on Earth, is actually becoming a problem because of anomalies in the form of two viruses, giant viruses that we found. One's called Megavirus chilensis, the other one's called Mimivirus. And these things are huge, and they contain an enormous amount of genetic material. And viruses aren't meant to do that. And if you plot the tree of life, how things are supposed to have evolved and how things develop in the history of life on Earth, you're not meant to have viruses with massive amounts of genes inside them. And so biologists are actually having to face now that they might have to redraw that whole tree of life and maybe put an extra branch on the bottom and try and work out where that story is going, all because of these anomalous observations. Sticking with biology, in fact, sex is a problem. And nobody knows why sex is so prevalent in the animal kingdom. Now, it's thought that sex helps you shuffle genes around, which helps you deal with a changing environment, and you might be able to cope with, say, disappearing food sources or whatever. But actually, cloning is genetically the most efficient way to reproduce yourself, and almost nothing in nature does that out of choice. But it outweighs, in theory, the role of sex enormously. There's another example I could give you in the universe that doesn't make sense, which is that the laws of physics seem to be changing or seem to be different elsewhere in the universe. And you have to get the data from distant quasars, the furthest things away from us in the universe. But what they tell you is actually the laws of physics over there, or when that light is traveling from the quasars to us, seem to be different from the laws of physics that we experience here now on Earth. So we're in this position where we don't really understand whether the laws of physics that we experience are actually just sort of cosmic bylaws, and the laws of physics might be somewhere different somewhere else in the universe, or indeed at some other time in the universe. So what do we do with all of these things? Well, the important thing to realize is that we need a new generation of scientists to be coming up and to be dealing with these things. Now, who's going to deal with this? Well, let me tell you, it's not going to be the old people. And I'm not just saying that to be rude about the old people, but when you work in science for a while, you become used to the fixed ideas that you've grown up with. And it's very important that you come at anomalies, things that don't make sense, with an entirely open mind and a new kind of attitude. And it's not just me who's saying this. Charles Darwin said this when he wrote The Origin of Species. He said, "I by no means expect to convince experienced naturalists. I looked with confidence to the future, to young and rising naturalists." And I'm hoping that that's some of you, perhaps here. And if you do manage to get to the point where you are working in science with your open mind and discovering that there's plenty left to do, rumors of the death of science have been much exaggerated, let me tell you. There's plenty of opportunity to move on to. I just want to make one plea, which is that if you ever get yourself into the position where you have a laboratory, can I ask you to put a quote on the wall of that laboratory? And that quote is from John Wheeler, a great physicist who was the PhD supervisor of Richard Feynman. This is the quote: "If you haven't found something strange during the day, it hasn't been much of a day." Why would he say something like this? Because actually he recognized that in science, the only things that matter are the things that don't make sense. Thank you for listening.